Hi, welcome to the Optical tutorials. In this video, we'll cover the format results module here. So this is the first module you're going to work with as soon as you're done with your analysis. So we already defined our parameters, we ran the analysis for a while, and now we want to look at our results. Okay, so let's get started. So the very first drop-down menu you have here has pretty much everything you would expect to see in a digital image correlation software. So U and V represents the displacements along respectively X and Y, just like the convention is usually in mechanics. And then you have the rotation, so a rotation for each subset, so a rotation map. Then you have the strains, EXX, EYY, and EXY. The principal strains, the principal directions, the von Mises strain, the Tresca strain, the correlation coefficient, which we're going to cover in a second, and then the X and Y coordinates, which are simply the coordinate of each subset. Not that useful to look at here, but when you export your results, it can be very handy to have this map in the form of a table usually, so that you can actually match your results to a certain location. Okay, so for this test, we would likely be interested into the shear strain here. And what we're looking at now, it doesn't look like much, right? It's just a big orange map. The reason is because these post-tensioning rods here created a lot of noise and a lot of wrong results. And so these wrong results are messing up the automatic scale of the software. And I wanted to cover how to overcome that in the simplest way possible, because this is a problem you're going to see a lot. So let's look at somewhere more advanced in the test. So here's a good example. This post-tensioning rod here has the red color, so the very top end of the color scale, and the blue color, the very bottom end. So because it has poor contrast and so on, and because the specimen is moving behind, whereas the rod remains straight, it creates some artificial strain. It is likely to be a really poor correlation in this location, but it still, despite the fact that it is a poor correlation, it still has a strain value. This strain value being so high, the rest of the image lies into this small range here, and that's why we can barely see anything here. So we need to adjust that. So two ways to do that. Let me show you just the most basic way, but also the slowest one. So here you have the lower band slider and the upper band slider. These two boxes here represent the minimum and the maximum of the sliders, not the slider location. It's important to know that. So when I'm moving the lower band here, I can see where my slider is by simply looking at the bottom of the scale here, right? And same with the upper bound. This value will not change because this is the maximum of the slider. However, when I move the slider that way, the top here changes as well. Okay, so I could simply go that way, get them as close as possible, and when they're getting too close and I feel like I don't have enough room here to do tight adjustments, I could simply crop or change the max value here. For instance, here the maximum value is 0.03. I can see that I am at 0.003 here, and still I'm not hitting the limits in the region I'm interested in, right? So I could set that to, for instance, 0.003. And now I have a lot more slider region to work with, right? Same with the lower band. So, let me fix that here. Here we go. And so now I can work in a much narrower region, so the sliders are much more accurate, right? So simply remember, these are the boundaries of your slider, not the boundaries, the bounds of your color map. These are the bounds of your color map, and to know their value, you simply look at this color scale here. Everything is live, very interactive, so very easy to set up. Now this is a complicated way where we just go trial and error and try to get the boundary where we want, where it does make sense. Let me show you a trick here. As I said earlier, I'm going to put everything back to auto scale. As I said earlier, the autoscale is messed up because of this post-tensioning rod here, and likely some other points maybe here, or if you look carefully, you will see in around these regions here, you may have some weird values. So it is also likely that the correlation was very poor here. So we can look at what's called the correlation coefficient. This is a map that tells you where you had a good correlation and where you had a poor correlation. Okay, 0 being the best you can get, right? So you can see that here it was an excellent correlation. That's good news because that's the data we're interested in. And the poorest correlation we had is here, and also here where there was some cables on the way. So that's okay because we don't care about this value here. However, you can see that when we have cracks in the specimen, it does also alter the correlation coefficient. Of course, now the correlation coefficient will not be as accurate, yet it is a region of interest for us. So we want to make sure we preserve that, right? So let's go back to our shear strain here. What I'm going to do is use this slider here. The title is correlation coefficient clipping. In other words, it will exclude every subset that has a correlation coefficient above a certain threshold. And just like we had sliders and a maximum here, I have the same here. I have a slider that I can drop down, and if the scale is too coarse, I can change the upper bound of this slider. There is no lower bound because the lower bound here is always 0. So I'm going to bring it down to 2%. And so now I have a lot more slider region to play with, right? And you can see that as I do so, the pre-stressing rods are starting to disappear. Let's go even to 1%, or I'm even going to put 0.1% and reduce that even more. So you can see that the regions where we had cracks start to disappear, as well as the region where the post-tensioning rods are. So here we have a blend of interesting data and non-interesting data. Meanwhile, the autoscale starts to make more and more sense. So one way to use the autoscale to your advantage is the following. You simply drag the slider and get rid of all the messed up subset who affect the autoscale, right? So I'm gonna go just to show you, I'm gonna go very low, say here. So now here I did lose my post-tensioning rods mess, but I also lost a tremendous region here of interest for me, right? So I need to bring that back. However, now the autoscale is fairly well behaving, right? Because now there is no ill-behaved subset, so it's working pretty well. So what I'm going to do is I'm just going to move that slider until I see an autoscale that I like. And then I'm going to switch to manual scale. So I'm going to keep these values now and bring the slider back up. Here we go. And I can even bring it back up to 2%. And that's a very quick way to set your manual scale to reasonable boundaries. So let me show you again. I'm gonna go to auto scale. Okay, so this is messing up everything. I drag down the slider until my auto scale looks more interesting, say here. Turn it into a manual scale and bring back everything. And then I'm in the ballpark now, right? So I can tweak it even more. I can bring that slider up and so on, right? So this is a very quick way to get your scale within bounds. Drag the slider to the left, switch to manual scale, and drag it back to the right. All right, so that's for the shear strain here. If I was interested in displacements, these displacements here are in pixels. But since we defined a scale in this module here, we defined a scale, I can look at the displacement in any unit I want. We define the scale in inches, but Optecal will do the conversion for you. So I can now have displacement in millimeter if I want to. Okay, I can also have rotations. So same here, we have noise. So I could adjust my scale by dragging it like this. bring it to manual scale and drag it back up. Okay, let's go back to the shear strain map, which is probably the most interesting for this project. Let's see what else we can do in this module. We have this slider here, transparency. So it's simply to get the color map more or less transparent. It can be interesting to see if you can see a crack visually in the picture. As you can see, there's no crack visible here. These are shear cracks. They are almost invisible even with a magnifier on the specimen. It's in the order of microns. However, optical captures absolutely every single one of them. So that shows the power of image correlation for this kind of experiment. Okay, so let's go down a little more. So now we have the coordinate system module here. So let's take a look at that. We can look at our color maps in the deformed configuration or the reference configuration. So if I hit reference, now it's not very obvious on that particular experiment, but we're looking at the original image, the reference image, with the color map overlaid on top. So if I look at, for instance, one of the very last images, I'm going to pick one where we have a lot of rotation. So here we had a lot of rotation. This is still not moving at all because we're looking at the reference image. If I click deformed, now we're looking at the deformed image, and you can see the color map will track your specimen. Okay, so reference versus deformed. Here we have the strain definition. So it's either material or spatial. So the green Lagrange strain definition or the green Almanzi strain definition. Both strain definition here are nonlinear. And yeah, by the way, the rotations are also large rotations. So this is not infinitesimal strain theory in optical. Everything can cover finite strain. So don't be shy to use this software to do plasticity and so on. The strain definitions are for finite strain, for large strains, in other words. Okay, so I'll refer you to your mechanics book to know in greater detail what this means, but if you're familiar with finite strain, you probably heard about them already. Okay, then we have more simple buttons here. The show axis button, so very simple, and the flip X and Y. So this is a very odd convention. It's a convention that comes from the image processing where X goes that way and Y goes down. So it's an indirect coordinate system. It is usually the coordinate system you will find in any image processing software. It is usually not the coordinate system we like to see in mechanics. Now, the neat feature in optical is that just like many other objects here, you can actually grab these axes and drag them wherever you want. So I'm going to display the U map to show you, for instance. So I'm going to drag these axes where I want them to be, and then I can also rotate them like so, and you can see that the maps actually update as we do it. So it is really amazing here. It is because optical works on the lighter scale images in order to allow this user responsiveness, right? So you can get it in this direction, and then you can also hit flip XY button in order to get what we usually see in mechanics books, and where x-axis goes this way and y-axis goes that way. So the kind of stuff we are more used to see. You can put it on center and make it disappear later, so it doesn't show in the middle of your map. You can put it at the corner of your specimen. You can put it absolutely anywhere you want. If your shot were a little crooked, you can actually adjust to make sure it's in the axis you intended to shoot your pictures at. And if you have an axis symmetric problem, you can actually go to polar coordinates. So that's a really, really neat feature. Obviously, this is not very suitable for this particular experiment, but you can switch to polar coordinates, and there is an example on the website of a rebar being pulled through a fiber reinforced concrete, where this polar coordinates option becomes very handy. Okay, last but not least, you have the filters here. So I'll switch to a strain map to show you. So we have a little more noise here, right? So I'll go back to an image where we had more sense. You can see that we lost a lot of the subsets here because of the large cracks. I can bring those back by bringing the correlation coefficients higher up. Here we go, they're back. And you can see that they are completely clipped here. They are completely into the blue and red. And oftentimes you will want that. You will want your cracks to be completely clipped in order to see the rest of the strains, which are, usually 100 times smaller or even less. You still want to see what's going on here, right? So usually you will clip your cracks in order to get the elastic strain in the back here within reasonable reading range. Okay, what you have here are just a couple of filters, median filter and Gaussian filter. I would strongly recommend that you don't use those too much. They're here just in case if you want your pictures to look more pretty, but you're necessarily affecting the results here, right? You're kind of hiding something that might actually be a real discontinuity. A median filter is really good filter to get rid of what's called the salt and pepper noise. So it's not an average, it's a median. That's why it can get rid of completely odd values very easily. Gaussian filter is a blurring filter similar to a camera blur. And so you can see that these images can look really smooth, really buttery. Again, I would not put too much of that because it is really kind of hiding the truthfulness of your experiment. So I will drag those back to the left. However, if you have very noisy results, if your image quality was poor, and you still need to do something out of your data, this is available for you. So you can use those and make your result look a little nicer. Okay, so that's it for the format results module. Every single parameter that you decide to use here will be then used when you export your results. So you should really pay attention to the parameters you're using here if you want your photos and videos to make sense when you export them later on. All right, thank you very much for watching, and see you for the next tutorial on post-processing tools.